to this class, and what we are going to begin today is basically a completely new topic, okay, and this is control chain processing. We have seen the kind of control information which is required for the physical layer data to get processed, and we are going to see that, okay, and that data, that control information also gets processed, that itself has its own physical layer, okay. So we'll see that. We'll first understand what is basically what kind of control information is sent, and then how it gets processed. Okay, you'll see that this physical layer processing, there are certain subtle differences between the file layer processing of physical layer data channel and physical layer control channel. Okay, so control processing is different from the data processing. Okay. And we'll understand why it is different and how it is different, okay, right? And as I said, even before user can decode its data, it needs to know that control information. And we just saw that, wherein like in order to read the data also from this two-dimensional grid, it needs to know that where it is located, okay, in two-dimensional grid. After that, it needs to know what is the MCS, right? The receiver needs to know the MCS. Okay, which is like, then only it can process. It needs to know the transport block size. Who's going to send all this information? Okay, and how is it going to send? Base station is of course going to send that to the user. Okay, but how is it going to send? Where is it going to send? That's the, like, we'll spend considerable time understanding that. Okay, right. So again, so this is, I keep coming back to it because that's the genesis of what we do. Okay, in the physical layer, and this is now we're going to focus on this control information. Till now we were focusing on this processing, okay, right? And so what is there? This is basically passes on the data payload, which is the transport block, and this control information is given a name. This is called, of course, DCI control information, but in the downlink, okay, it is called downlink control information. Fine, okay. So that information is called DCI, okay, and it has to undergo physical layer processing. Okay, because this information also needs to be transmitted on air, right? As I said, MCS, user needs to know before it can process the data transfer block. It needs to know what is the size of a transfer block. Okay, so that information is also transmitted on air after physical layer processing. Okay, DCI, as I said, few things, few parameters which we know: MCS index, number of resource blocks. Then where are these resource blocks allocated in this grid? Okay, user needs to know. These are very simple parameters, but there are other complicated parameters also, okay, which we'll see. Okay, so what physical layer does is first it uses this information to encode this data. Okay, then it transmits this information also as along with data or prior to data. Okay, right? When I'm saying physical layer, this is PDCCH, physical downlink control chain, not PDSCH. Okay. Right, this PDCCH chain, what is it does? It encodes DCI. What is DCI? It is not transfer block, it is this control information, okay, which gets encoded again at a particular rate, okay. And so in principle, this rate should be similar to this rate because that's what user has asked, correct? Okay, or lower than that because you want to give, as I said, more protection to this, right? Another key thing here is you will see, okay, the control information size is of the order of few tens of bits. This can run into thousands of bits or lakhs of bits. Okay, right? So that also changes the design philosophy of this control chain. So it encodes DCI at a particular rate, performs again rate matching, interleaving, scrambling, 4-QAM modulation. Other key difference here is there is no adaptive modulation. So control chain only uses 4-QAM, okay, because it has to be robust to the noise, right? So that's where we use 4-QAM. 4-QAM is the most robust modulation scheme to the noise. Okay, it can work at a lower SNR, that's what we are saying. Okay, right? So it does this, and you'll see this, the philosophy, more or less there are similar looking modules, okay, but their design philosophy is completely different. Fine, so let's see that. First, what I'm going to show you is what is actually contained in DCS, how it is defined. Okay, right? What are the different fields? Some of them we know. Okay, but we'll discuss them in a little bit more detail. And this DCI is carried over PDCCH channel. So what are we doing? This is the information DCI. Okay, it needs to be transmitted on frequency time grid. Okay, and this channel basically is called the PDCCH channel. So another aspect is basically DCI is used for both downlink and uplink scheduling. What am I saying here? Okay, as we just learned that the base station is the controlling authority. Now it will send, not only send the downlink data and the control information, okay, it will use this DCI to inform the user when it should send its data. What should be its MCS? On what resources it should send its data. Okay, that information is also sent by the DCI. Okay, right. So DCI has two jobs. Okay, one is to basically help the user in decoding the downlink data. Okay, and other job is to schedule the user in the uplink also. Okay, because who is scheduling? UE cannot transmit the data on its own. That information, okay, what MCS the UE should use, okay, where it should transmit its data in this two-dimensional grid. Again, base station decides that. And how does it send? DCI. Okay, right. So there are multiple DCI formats. Okay, what are these formats? Okay, I am giving you one example. This is DCI format 10. Okay, there are other formats which will come. Okay, we'll see that. Okay, which is used for downlink. This is used for downlink scheduling. And what is contained? Length of this format is around 35 bits. Okay, first difference we see. Only this needs to be encoded, not thousands of bits. Okay, so you need a forward error correction code which is basically works at these, which can give you good performance at these small code block lengths. Right? Okay, so you'll see that encoding is completely different. You use a different encoder for this PDCCH chain. Okay, so what is contained in this? The first thing is modulation encoding scheme. How many bits you will require to represent modulation encoding scheme? How many different indices were there? 28 to 30, right? Okay, you need 5 bits for that to represent one of these MCS indices. Correct? New data indicator, again it is hybrid ARQ. Okay, it explicitly, base station explicitly indicates the user whether it is fresh transmission or the old transmission, using this to enable a hybrid ARQ. Okay, right. So which redundancy version is being transmitted? Again, 2 bits, because there are 4 different redundancy versions. That's, see, you are that precise. Okay, you cannot really, like, because this is all control information. It is overhead. You want it to be as minimum as possible, okay, because you are sending this at the expense of data. Okay, which finally is not useful, because you are going to watch a video. This is going to help decode the video, but not the actual video. Okay, time domain resource assignment, where in which symbol the data is being transmitted. That's the time domain resource log. Okay, so now there are only, like, how many symbols are there? 14 symbols. You need 4 bits. Okay, frequency domain resource assignment, it is like you need variable number of bits. I'll show you that. Okay, why it is variable. Okay, then what is this? Identifier for DCI format. By this DCI, whether it's like doing the downlink assignment, it's helping the data, downlink data to get decoded, or it is an uplink grant. Okay, uplink grant means if it is used for uplink scheduling to inform the user that you should use these parameters to encode your data. Okay, then the same DCI, as I said, is used for uplink scheduling. So if it is, let's say if it is 0, it becomes downlink assignment. If it is 1, it becomes an uplink grant, right? So that's how it is differentiated. But there are multiple other fields also. This is what at least we understand till now, right? This is, what is this? What am I telling you here? This is DCI content. Okay, this is the information which basically is required to decode the data and encode the data in the uplink. Okay, but decode the data in the downlink. Okay. So same DCI is used, and that's how it is differentiated. Okay, few other fields which we are not, like, comfortable with. I have not introduced you to them, but let's see this. This is how it is defined. Okay, I will not get into these other fields. Okay, but let's see this, how it is. This is, what are we doing here? We are comparing 2 different DCI formats for downlink. Okay, this is format 10. This is format 11. What is happening here is, this is used for MIMO transmission. This is used for basically single layer transmission. Okay, right. So most of the fields are same. Okay, what we understand here is, look at this. What are different fields in this? This is, as I said, 30 to 35 bits. These fields we know: MCS, new data indicator, RV. Right. Okay, and what is this? If it is MIMO and you are sending, like, second transport block also, you need to send the same information for that also. Right. That's why I said, if it is, you are not doing that, then it is format 10. because these, you don't have to send this information, it's extra information. Okay, right? So different formats. Okay, that's why they are defined, because you want to be like very, very optimized with respect to any information which you send on air. Okay, right? So this tells you, this gives you a kick, okay, how optimized our systems are. Okay, then look at this, when some of these things we understand, frequency domain allocation, right? Where is the data is scheduled in this frequency grid, okay, time domain allocation. I will not get into all this because this is like, I have not taught you still, but there are these fields, okay, which have to be told to the user before it can decode its data. Okay, then there is something related to multiple fields related to, again, more fields related to multiple antenna. Say they are here only. Okay, we are not going into this because we have not studied them, but these are the contents of the DCI, right? So this is for downlink, same as for uplink. Okay, format 00, format 01, right? So see, and what is happening here? You see this, okay, that there is only in the uplink that one thing which is immediately clear, you can only send one transfer block on the uplink side. Okay, maximum one transfer block. So no field for the second transfer block. That's one difference. Okay, again it's DCI only, right? But used for uplink grant, used as an uplink grant. Okay, so frequency domain allocation, time domain allocation. Other fields I am not telling. Okay, but this information, this kind of information needs to be passed on. Okay, MIMO related, power control related, how much power the UV should transmit. Okay, right? So that's what it is. All this is neatly defined. Fine. Okay, and you could basically, if you could have a cheaper mobile which does not support this MIMO capability, it doesn't have to implement that, so it becomes cheaper, right? Why should every mobile be an iPhone? 4,000 rupees mobile which doesn't have to implement this. That's how you reduce the cost. Okay, cheaper ICs to basically which will not implement this, some of these features. Correct. That's how standards are designed, so that like, there are different varieties of handsets. Okay, and how do you reduce? This is one. Of course, other things are also there. Okay. Fine. So this is what we have covered in this lecture till now, is basically what are the DCI contents. Okay. Another thing what we have understood here is that DCI is used for downlink scheduling as well as uplink grant. Now see this in this part of the class, I'll show you how flexible DCI is. Okay, right? And then what do you do with this? How do you, like, when is it sent? Okay, that's the focus of these few slides are. Okay, so what are we going to discuss now is how this DCI basically schedules the user in the downlink, okay, in the time domain. What is the time axis? Symbols. Okay, what is the frequency axis? PRBs. Correct. Okay, and there is a separate field for time domain, there is a separate field for frequency in the DCI. Correct. Okay, so that's what we will see now. Okay, so what is this? Let's say this is some general nth slot. Okay, it can be any 0th, 1st, or okay, so any generic slot. So what are we saying here? Okay, so what if you look at this? Okay, what is this figure telling us? Okay, DCI is coming in nth slot. Okay, it is not necessary that the data needs to come in the same slot. Data can come later also. Okay, and it can come in the same slot also. It can come later also. Okay, right? Because user should be prepared to decode the data. Okay, most of the time what happens is DCI comes along with data. Okay, in the same slot, but it is not guaranteed that it will, like, data, DCI and data will come together. Okay, as I said, it can come in advance. Okay, and what are we looking at? We are looking at this time domain allocation. Okay, what is the time domain? What should it indicate? What is the, like, units which we have? Symbols, right? Okay, so what is it telling? Okay, that it will indicate like how much is this slot offset. Okay, this slot offset from where the DCI is coming and from where the data will come, PDCCH will come. It will give that offset. Okay, if it is coming in, this DCI is coming in nth, it can come in n plus 4th slot also. Data can come in n plus 4th slot also, right? And in that slot where this data is located, what is it telling? This is a start symbol, and it will have these many, the data will come for these many contiguous symbols after this. So data is going to begin at L symbol and it's going to begin at S symbols. S is the start symbol. It's going to continue till L symbols after that. Okay, right? So that's how the data is scheduled in time domain. Do we understand this? What I was saying is very simple. Okay, that for two things, that PDCCH can come in a different slot than a DCI, where the DCI is coming. Okay, and how will DCI schedule this data in downlink in time domain? It will tell what is it going to tell, what is the start symbol and what is the length of number of consecutive symbols after that where data is coming, right? Okay, I have told you that. Okay, that this is, so this is basically, this is K0, it is not shown here. Okay, this offset is K0. What are we saying here? Slot allocated for PDCCH is determined by n plus K0. N is this slot and PDCCH will come at K0 slot after n. Fine. Okay, this is this. Okay, K0 is the offset relative to the slot where DCI was obtained. Fine. Okay, it's not an absolute slot, it is the offset from where the DCI is obtained. That's all. Okay, right. So example allocation could be with start symbol of S and L is equal to 4 consecutive symbol and a slot offset of K0 is equal to 1. I am giving you one example allocation. Okay. What is K0? K0 is 1. Right? PDCCH will come after one slot where DCI is transmitted. Right? And where is it going to come? Data is going to begin at S is equal to 3 and it will go on till L is equal to 4 symbols. It will look like this. Okay, DCI is somewhere sitting here. User will decode its DCI. It's not an easy job to decode DCI. We'll see that also. Okay, right? Once the DCI is decoded, what will this DCI tell? It will tell that, boss, your data is located here. Okay, that it is located in K0 is equal to 1. And so this is the slot which follows this. Okay, and it is located at symbol number S is equal to 3. 0, 1, 2, 3. Third symbol, and it goes on for 4 OFDM symbols after that. This is your data in the time domain. I have to still tell you how much is there in the frequency domain in this axis. That will come later. Okay, right? So that's what it is. So, and what are these values? Okay, how much you cannot really, I mean, there has to be some limit. There cannot be an infinite delay. It cannot be like very large because then user will keep waiting for its data, right? Okay, so this slot offset can be from 0 to 3, K0. So what is, if K0 is 0, what does that mean? Data will come in the same slot. Okay, and then, okay, this is for downlink, and for uplink, because this is used for uplink also, right? This DCI is used for uplink grant also. There the offset of 0 to 7 can be used. Okay, two different numbers. Okay, and not all combinations of start and length fit within one symbol. What are we saying here? That if it indicates that data is beginning here, the data has to end in the same slot. It cannot spill over to the next slot. That's the limitation. Okay, right? That of course puts certain limitations on what S can be and what L can be. You cannot begin at, let's say, L is equal to 12 and say that, you cannot begin at S is equal to 12 and cannot say that L will go on for 4 because slot is only of 14 symbols. That's the common sense. Okay, right? So, for example, starting at OFDM symbol 12 and transmit during 5 OFDM symbols obviously results in crossing the slot boundary, and this is an invalid combination, right? So, data which this DCI is indicating cannot spill over from one slot to other slot. Okay, so data can of course begin at S is equal to 0 and can go over the whole of this slot. That can happen. Okay, right? So that's how DCI is actually configured, right? So this is the table. This is the table from the standard. What is it? Look at this. How many such possible combinations are there? Without going into all this, okay, this I have not taught you, please don't go into this, okay. What is this? 16 different combinations. I said, right, 4 bits. For time domain allocations, how many bits were we using? 4. And it will be one of these indices, which will be indicated to the user, and user knows this table, okay, right. And look at this. So what is this? Look, mostly this is the table. This is what we are comfortable with, but as I said, there are 3 more tables like this. And what is this? Here, what is the unique thing about this? K0 is 0. Data will come in the same slot. But there are other tables also where K0 is different. Okay, right? Here, what are these different combinations? Data begins at 2. Start symbol goes up to it occupies the whole of the slot after that. And then a different combination. You will see that data is never beginning at S is equal to 0. Why? Because most of the time that symbol is occupied by DCIs. And it is beginning at 1, okay, but mostly it begins from 1 or 2, but not from 0. So DCI also needs to be sent, okay, right? This is what is like one of this will be indicated using those 4 bits. Okay, there is a time domain allocation, right? Okay, fine. So same thing, BS inform the user in the uplink when to transmit. Uplink scheduling, same DCI, okay. DCI is used to schedule users in the uplink also. Informally, it's called, if you talk to a guy who is like working in standard day in and day out, he'll say uplink scheduling grant. When DCI is used for scheduling uplink. Look at this, same, okay, same idea. DCI, this is offset, PDCCH, like it is used to schedule uplink data. Uplink data is called PDCCH, not PDCCH. Okay, so what are we saying? It is used to schedule PDCCH. And what is this? The idea remains same. SL offset K0. Okay, it is called K2 here. Sorry. Okay, this is K2. Okay, there is a table defined in the standard. What is this? Forget. So this is the offset. Okay, J. If I set J to 0, okay, it needs to be. It will not be 0 because user will first receive this DCI in one slot. Okay, it could be. Okay, because if it is an URLC user, you decode the data and send that, decode the DCI, send the data in the same slot, right? Okay, if otherwise it will be scheduled later. Fine, so that's what it is. J is also defined in the standard. J can take 0, 1 values. Okay, I don't remember that, but that it's like it can take values from 0 and subsequent other values also. Okay, so what is this? S and L 0, 14. Same idea, right? Again 16. 4 bits are there. You don't want to have different combinations, different number of combinations in uplink and downlink because you are using the same 4 bits. Correct? Okay. This is the time domain allocation. Fine. So we have understood time domain allocation. Let's look at the frequency domain also. Okay, right? So as I said, users need to know where are they located in the frequency domain also, right? So there are 2 different kind of allocations which are used to schedule users in the frequency domain. Okay, they are called type 0 and type 1. Each one has its own use. Okay, there is no such type 0 and type 1 for the time domain. For frequency domain allocation, there is type 0 and type 1. What are these types? Okay, so what is it says? Type 1 basically what it allocates is contiguous PRBs in the frequency domain, right? Starts from, let's say, any location, PRB 25, and how many locations after that you are transmitting. The data has to be transmitted in how many PRBs you are allocating to this user in the frequency domain, correct? Okay, so what it does is it encodes both this information, starting position, where is starting, which PRB you are beginning from, and how many PRBs you are using after that to send the user's data. All this is, there is a formula which encodes both this information in a single number. Okay, so what does it do here? So this is called RIV, resource indication value. Okay, right? What is this resource indication value? Starting position, this is the starting position, and how many contiguous PRBs you are allocating to this user. All this length and the starting position, there is a formula, it can be encoded, it can be like you can come up with the formula, okay, and then that is the information you are going to send. As I said, the frequency domain field was variable, right? It was not 4 bits, so there is no such table defined for the frequency domain, okay, right? So what is this? But you are like, what are we saying here? This kind of allocation can only schedule contiguous PRBs in the frequency domain, right? Okay, so let's say 20 PRBs, 50 PRBs, but contiguous. Okay, let's say I don't want to do that. I want to allocate PRB 0 to 9, then somewhere at the end, because I know those channels are good, right? I don't want to assign these contiguous PRBs, but this is basically used to make contiguous assignment. Okay, right? And this is one kind of assignment. Okay, so this is called RIV, resource indication value. Another one is called bitmap based allocations. As I said, okay, this is only contiguous, right? Don't want to do this contiguous allocation. Can you do non-contiguous allocation with this? There is no option, because starting point and the number of contiguous PRBs after that. That's what you can assign. Suppose there is a need to assign non-contiguous PRBs. We'll talk about that probably in the next class, why do you do contiguous allocation and non-contiguous allocation. But let's understand this today. There are 2 different requirements, okay, allocating contiguous PRBs and non-contiguous PRBs. This will allow contiguous PRBs. What is, if you want to allocate non-contiguous PRBs? Okay, right? Don't look at all this, I'll tell you what it is. Okay, what is this? Okay, what am I saying here? What is the objective here? The objective is I want to allocate these two RBs to then these two PRBs or these three PRBs and then these PRBs and these PRBs. Okay, I am calling this as not PRBs, I am calling this as RBGs. Okay, I'll tell you that also. Okay, RBG is basically a group of PRB. Okay, but for understanding initially, let's say I want to allocate this PRB, this PRB. Okay, right? I'll define this also appropriately. So what am I saying? This is a, look at this. This is a bitmap based allocation. What is this bitmap based allocation? For each of this PRB, there is a bit defined. If this is 1, it will be basically this is assigned to this user. If it is 0, then it is not assigned to this user. That's all. Depending on this bitmap values, user will be able to know what are the PRBs for now which are assigned to this user. But I can allocate non-contiguous PRBs, right? Okay. Now what is this RBG? Okay, it's a group of PRB. Now if you do this PRB based allocation, how many bits you will need? You will need 275 bits. Well, how many PRBs are there? 275 bits. 275 PRBs. So you will need a 275 bitmap, long bitmap, which is humongous. Okay. Right. So what you do is you group these some number 3, 4, 5. Okay, that you assign together because you want to like have some reasonable overhead, reasonable length of this bitmap. Okay, right. So that's what you do over here. So you group these RBs together and call them RBGs, resource block groups. Okay, right. So and what is it? Indicates, so that's what it's indicating. These arrows are indicating that these RBGs are assigned to this user. 1, 1. So you see this grayish. Okay, these are assigned to this. Okay, again grayish. So this bitmap is 1, 1. Then 1 is, this is not allocated. This is, it should 1 more 0 should come because 2 RBGs are not allocated. Okay, right. So indicates sets of resource block groups that you is supposed to receive in the downlink. Okay. Size of bitmap is equal to the number of resource block group in the bandwidth part. Okay, I have not introduced this term. Okay, let's stop here. Okay, I am saying how many resource block groups are there in the bandwidth. Okay, in 100 megahertz bandwidth. Okay, let's say just for example, there are 275 PRBs. Okay, I club 5 PRBs together. So 275 by 5, these many PRBs are resource block groups will be there. That's the idea, right? Okay, so the bitmap will of course reduce by a factor of 5. I make divided by 15, I divided by 20. Resource block group size is going to increase, but granularity is reducing, correct? Because then you can assign a minimum of 20 together. Okay, right? Otherwise, if it is 1, you want that kind of granularity. It's typically not done. You need 275 bitmap. Okay, right? So now what is this bandwidth part? Bandwidth part is basically what is happening here is, I'll quickly introduce this. Okay, what is the bandwidth part? Let's say 5G doesn't talk only in terms of bandwidth, which is 100 megahertz. Okay, 5G is supposed to be serving different kind of devices. Let's say there is an IoT device, okay, which needs to send few bits of data. Why should it be designed for 100 megahertz? Okay, right? Because you want the device to like work forever. It needs only few bits of data, so it should be designed for, let's say, 2 megahertz. Okay, so 5G says, okay, it defines that, okay, though you have 100 megahertz of bandwidth, you can suitably define bandwidth part. So that particular system will only understand, okay, all the system, 5G system, they work in terms of bandwidth part. Okay, if it is sophisticated mobile, bandwidth part will include all the PRBs. If it is low-end mobile, it will include for very few PRBs. Okay, so for an IoT device, this is the bandwidth part. So this is the bandwidth for which it is designed. So the iPhone is designed for this, or any other mobile, but IoT it is designed for this. Okay, right? You see this because number of PRBs for this device is low. So look at this, 2 of them will be clubbed together. Okay, and the resource block group is formed. Okay, but if there are so many PRBs, then you club 16 of them together and then form a resource block group. So 2 different configurations. Okay, 8, 16 remain same. Okay, once doesn't matter. But if there is smaller, if there is simpler device, right, you want to give little bit more flexibility. Either you can club 2 of them together or you can club 4 of them together. Okay, right? So that's how it works. Okay, so as I said, to conclude, it was variable, right? Frequency, domain, bit, field was variable. Why? You understand this. Can you type 0 or type 1? Type 0 has different length than type 1. Even within type 1, it has a different length based on how many bandwidth part the system has, right? So we'll stop here. We'll continue discussing this in the next class. And what we'll be discussing in the next class, how this DCI is processed. Now I have told you how this DCI is designed, right? What are the different fields in DCI? But how is it finally going to be transmitted on air? You need to process this at the physical layer again.